Welcome to our 5-part video series on sustainable design using cold-form steel. This module addresses the thermal performance of steel products for sustainable buildings. View the other modules in the series for more information on sheet steel building products and sustainability. This module will cover features of an energy-efficient building envelope, insulation in CFS walls, thermal bridges, thermo-graphic surveys, thermal mass and steel, air tightness, and urban heat island effect and cool roofs. Energy-efficient buildings require that many factors be addressed, including an appropriate building envelope with high R values, high-quality glazing, daylighting, and efficient HVAC and lighting systems. Thermal efficiency factors in building envelopes include high insulation levels, airtight construction, minimum thermal bridging, appropriate thermal mass, and good air and vapor barriers. LEED requires that all buildings meet minimum energy performance standards. For new buildings in Canada, this represents either a 23% reduction in energy costs below the Model National Energy Code reference building, or a 10% reduction in energy costs below ASHRAE Standard 90.1-2007. Additionally, LEED Optimized Energy Performance Credit offers up to 19 additional points for new buildings if energy costs are further reduced. Standards for major renovations are less demanding. CFS components are widely used in envelope systems of qualifying LEED buildings. Integrating insulation into CFS walls. Lightweight steel framing envelope systems using CFS require appropriate design of thermal insulation and air tightness to ensure good performance. CFS has high thermal conductivity, therefore significant insulation outside of the steel frame is required to reduce thermal bridging. Ideally, the value of insulated sheathing should represent at least 25% of the wall's insulation value. Insulation is required between studs. A continuous air barrier further reduces heat losses by air leakage. With proper insulating techniques, R values above R20 can be readily achieved. This diagram illustrates how good design using lightweight steel framing can minimize thermal bridging and achieve high thermal performance. Thermal bridging occurs with all construction systems at lintels, corners, and openings. Due to the high thermal conductivity of steel, careful detailing is required for lightweight steel frame walls. This thermographic image shows variations in the surface temperature of a lightweight steel frame wall, indicating where additional heat is being lost through thermal bridges. Temperature variations across the entire wall only measure about 2.5 degrees Celsius, demonstrating how the external insulated sheathing significantly reduces the effect of thermal bridging. The dark color of the window indicates that its surface is cooler. Some thermal mass can reduce the need for cooling and improve heat storage. However, too much mass can lead to long warm-up times and temperature control problems. It's appropriate to integrate some thermal mass into steel buildings, as it will reduce the strain on heating and cooling equipment and help achieve a more consistent and comfortable indoor temperature for occupants. This can be done with heavyweight components such as concrete floor slabs, mass components such as fireplace walls, or alternatively with new materials such as phase change crystals embedded into drywall, which can provide sufficiently effective thermal mass. Air tightness is an important factor in reducing heat loss through air leaks, both for environmental and economic reasons, as well as for the comfort of occupants. As with all construction systems, air tightness in light steel framing can be achieved by careful detailing and good site practices. Air leakage occurs in all buildings through openings, cracks, and gaps. CFS construction can be designed to achieve high air tightness standards. Proper sealing of air and vapor barriers is required. The Canadian R2000 energy standard for housing requires an air tightness of 1.5 air changes per hour when tested at 50 pascals pressure difference using a blower door fan. Lightweight steel framing has been used in many R2000 houses, demonstrating that high airtightness standards can indeed be achieved. Roof construction must address overheating problems occurring in built-up areas due to the absorption and retention of heat by hard, dark-colored surfaces. Lead points can be scored by using roof surfaces with a solar reflective index of at least 78 for a low-slope roof or at least 29 for a steep-slope roof. Steel roofing and cladding materials that meet these requirements are readily available. Sheet steel products can contribute to the following energy and atmosphere and sustainable site credits for LEED Canada NC. Minimum energy performance prerequisite 2. Buildings incorporating sheet steel building products can achieve high thermal performance and airtightness, helping attain the prerequisite minimum energy efficiency levels. Under Optimize Energy Performance Credit 1, thermal performance can be further improved to earn additional points. Both Prerequisite 2 and Credit 1 require that buildings be designed beyond the basic parameters of either the Model National Energy Code reference building or ASHRAE Standard 90.1. Steel sheet building products can work within these parameters. The heat island effect roof includes 1 point for low-slope roofing with a solar reflectance index equal or greater than 78, or a steep-slope roof with a solar reflectance index equal to or greater than 29. Steel roofing and cladding materials that meet these requirements are readily available. Need more information on using cold-formed steel in sustainable design? Watch the other 4 modules in this series, explore our website at cssbi.ca, or call us at 519-650-1285.